Right, excellent. So I had thought it was time to bow out, but Nella suggested the topic of the history of speleothem science. So here I present just a few personal thoughts about the history of speleothem science, and I've tried to find ways to make them relevant to your work as scientists today by highlighting the generic issues of how the science progresses or otherwise. Let's brainstorm what held back the development of speleothem science, identify some issues, and ask if any of these issues are still relevant today. Stick with what we know. For quite a long time, paleoclimatologists in general tended to shy away from caves and stuck with better known archives, which were progressing very nicely, thank you. After all, speleothems are weird, and not even carbonate petrologists had bothered to study them much. Besides, there are too many sources of uncertainty. And aren't caves meant to be protected? Caves are too precious. It's been said that processes are kinetic, and more broadly that caves are too complex. Besides which, I don't want to have to master a whole bunch of physics, chemistry, biology just to do some paleoscience. And anyway, look at how no two stalagmites are alike. There is too much spatial variation. In fact, caves are unfathomable. And you want me to actually go there? Caves are dirty, wet, and claustrophobic. Now, in the early days, there were remarkable examples of quite heroic research in cave systems to understand the context of speleothem formation. Here are some of this pioneering generation, overwhelmingly male, but also highly experienced cavers as well as excellent scientists, whether from a background in geology, chemistry, physics, or physical geography. The next generations of speleothem researchers are more balanced in gender and ethnicity, and include those who have been caving since childhood and those who have come into speleology as adults. But there is still space for those who do not leave the laboratory. What those first generation scientist cavers were doing was trying to understand the workings of the cave environments involving the underlying physics and chemistry. Take, for example, the special issue of Arctic and Alpine Research in 1983, describing results of study of Castleguard Cave in the Canadian Rockies, facilitated by Derek Ford with participants including Tim Atkinson and Peter Smart. It takes 24 hours to reach the end of the Castleguard system, and then you find yourself beneath thick ice of the Columbia ice field. In one of the published studies by Atkinson et al., the physics of air circulation was studied using radon measurements and the role of geothermal heat transfer modeled. Using a physical chemical approach, Atkinson et al. In a second paper modeled the mysterious way in which speleothems form in this cave, despite the lack of an organic soil above the cave to drive excess limestone dissolution. Oxidation of pyrite generating sulfuric acid provides the main mechanism to drive limestone dissolution, a mechanism now known to be important elsewhere. Now, I'd like at this point to pay tribute to a wonderful paper by Holland et al. In 1964. Dick Holland was a geochemist who later took in the whole of Earth history in his amazing book, Chemical Evolution of the Ocean and Atmosphere. But this paper, summarized in the long paragraph, went to a great deal of trouble to obtain good data from the cave environment. So in those 3 caves in Pennsylvania and Virginia, they estimated the minimum necessary pressure of CO2 to reach the maximum calcium and magnesium concentrations observed. They observed that cave waters become supersaturated by CO2 degassing rather than evaporation in that case. They used the evidence that magnesium was constant in different parts of a cave, but calcium varied, and reasoned that evaporation would lead to an increase in magnesium concentration, whereas degassing followed by calcite precipitation would lead to little change in magnesium. And they also overcame for the first time significant analytical difficulties to explore how the strontium-calcium ratio in drip water evolved downflow. owing to precipitation of aragonite and calcite. So they've clearly articulating the concept, which was later known as prior calcite precipitation. And yet they started off as laboratory experimentalists who migrated to the underworld. Likewise, I had never entered a cave purposefully until 1994, as has been said, by invitation from Silvia Frisia and Andrea Bazzato, and was soon working with a variety of collaborators tackling similar issues to the pioneers, but with the benefit of mostly more sensitive and user-friendly analytical resources. Now, my focus has been primarily on processes and seasonality issues, but the mainstream of speleothem science, of course, has been the generation of paleoclimate records, for which dating is key. Here is the summary of an interesting exercise that I used with students a few years ago. Here are 20 events in the history of quaternary science. Well, I won't give you time to read them all, but you can look at them later. Can you put them in the right order and match them with the ticks in the timeline above? In the context of the current talk, the question is, how much did the science of dating archives have to advance in order to facilitate these discoveries? And actually, time is crucial to most of them, and therefore dating was crucial too. The roots of uranium-thorium disequilibrium dating lie in the 1950s, and the technique was more widely established applied to corals in the 1960s, which, being composed of aragonite, have much higher uranium contents than calcite. The method used required counting individual decay events using alpha spectrometry. And we see here the state of the art reached in the late 1970s for calcitic speleothems in this paper by Atkinson et al. In Nature, where the error bars were 10 to 20%. But there was a sustained effort to use isotope dilution mass spectrometry to measure the isotope ratios directly. And a breakthrough paper by Edwards, Chen and Wasserberg in 1987 established its feasibility, and much lower analytical uncertainties resulted. Fast forward to 2009, and Larry Edwards with HighChain has established a world-leading lab at the University of Minnesota, attracting many visiting scientists. I happened to be passing through there in 2009 on the day their latest paper on dating Pleistocene phenomena was published, and High is showing off the dramatically reduced errors in their enhanced multi-collector mass spectrometric approach. There's the old errors, there's the new errors. 50 to 100 years 2 sigma error at 130,000 years. Meanwhile, there's been increasing use of annual lamini in stalagmites. Here are some annual lamini in this picture, and you can just about see them in the lower image as well. These the use of counting annual lamini provides interval dates, which enhances the quality of higher resolution records. For example, in this graph on the upper left, you can see a one-to-one slope of age versus the lamina count, and then there's a hiatus, and then there's an offset, and you go back to the one-to-one slope again. Winding back to the early 1990s, we see the development of holistic approaches to developing speleothem records by Israeli researchers. Here, in 2 early papers on Sorek Cave, led by Mira Matthews, we can see how they've constrained the isotopic and hydrological characteristics of individual drifts and established, for then, high-resolution speleothem records of paleoclimatic significance for both oxygen and carbon isotopes. The dramatic carbon isotope shifts that you can see in the center of the lower diagram are linked to a specific Mediterranean rainfall climatology, as is the difference between glacial and interglacial oxygen isotopes. In these and other records, we progressively see recognized the role of water composition as the key control on speleothem oxygen isotope composition, whereas the original paradigm was that temperature was that control. So this increasing realization was aided by significant investment in techniques to extract water to measure its isotope composition. So in climatologically sensitive regions where rainfall oxygen isotopes are a function of rainfall amount or seasonality and vary in response to longer-term drivers, a picture emerges where speleothem records follow the large-scale atmospheric patterns, and oxygen isotopes become a climate parameter. And this climate parameter later becomes incorporated into general circulation models. The data shown here, compiled by Judd Parton, demonstrate the clear inverse relationship north and south of the equator in terms of changing solar insolation during the Holocene. Now, if we return to the barriers in progress, to progress in speleothem science, stick with what we know, that represented the prevailing viewpoint during the 20th century, during which fantastic advances were made in paleoclimatology through study of a wide variety of Holocene archives, including peat and lacustrine sediments, and records of glacial interglacial fluctuations, primarily through deep ocean cores and ice cores. Cave workers were getting frustrated that their records were not being taken seriously. But eventually, the advantages of speleothems were demonstrated. For example, we pointed out that caves are global and they're on land. Lots of good studies started to be published with excellent dating, using both absolute approaches and later interval dating approaches. And it was also able to be established that speleothems record both large-scale climate and local environmental change. But nevertheless, people had to have faith, and in the early 1990s, there was much interest in the long-term records from this place. Devil's Hole in Nevada. Here this is a tectonic fracture which allows access to regional groundwater. And the record you can see there was obtained by Weilegrad et al. At the USGS, and it appeared to contradict the ages for glacial terminations obtained from ocean cores. The ages were slightly different. However, these are not typical speleothems, but they're extremely slow-growing deposits from regional groundwater. But nevertheless, the power of archives that could be dated by uranium series methods was clear. Much later, the Innsbruck group in Mosley et al.'s 2016 paper found differences in groundwater use uranium series composition at glacial terminations, allowing a reconciliation with the oceanic record. Now, Nick Shackleton, you can see him on the postage stamp up in the upper right there. He was a prime elucidator of the meaning of deep ocean core paleoclimate records. Now, I only had a significant conversation with him once, in the course of which he revealed that he had been on the panel which approved the first European funding for a speleothem project. This was a project led by Frank McDermott and Sylvia Friesia, in which I was involved. And this project innovated in various ways, including a multi-proxy approach to records linked to cave processes, and it embraced speleothem petrology. It is so easy to get frustrated with the difficulties over getting or maintaining funding, but the whole system depends on scientists with integrity making wise decisions. Nick said, "We thought it was timely to give cave deposits a chance which has been richly grasped since." What about speleothems are weird? Well, the weirdness got explained. For example, the microstructural fabrics that we just saw some pictures of by Sylvia Friesia. The types of annual lamini were explained by Andy Baker. The chemical structure of annual lamini by me and Pauline Treble and Andrea Bazzato. And Wolfgang Dreibrot explained the shapes of stalagmites from theoretical modeling. However, the stalagmite that you can see here, which comes from Refugio Cave in southern Spain, really is weird. In this cave, there are many abrupt hiatuses, in between which it grows very quickly. Emily Macmillan concluded that the hydrology was disturbed by intermittent seismic events. So this speleothem ended up being too complex to publish in detail. Now, on the other hand, some speleothems are really simple. Many Chinese caves have large horizontal passages within which large diameter stalagmites have fantastic records. Just look at the potential for high resolution records in this sample. And some stalagmites are almost perfect. The red line you can see there joining the data points is the age model, depth versus age, and this stalagmite grew at nearly a linear rate for 9,000 years. So things are often easier than you'd think. Speleothems are not always weird. There are different approaches to dating. They provide constraints, and new and varied analytical techniques allow insights on causes of variability. But we also need to be realistic about both new techniques and the difficulties in maintaining laboratories. Now, here is a group shot of scientists in an early project, and you'll spot the guy with the white beard there. This is the eminent isotope geochemist Antonio Longinelli from Trieste. I remember his boast: "In my laboratory, there are 4 mass spectrometers, and none of them are working." Now, this slide is in praise of both the conceptual approach, but also the value of collaborative projects. Our 2006 paper, outlined here, was a great product of our discussions in drawing out a contrast between the simple cases where the atmospheric source signal dominates versus the other cases where it's really advantageous to understand cave processes. In fact, the collaboration extends beyond individual projects towards a supportive approach of the whole community, which in the 1990s and 2000s was particularly notable in Europe and Australia, and which was enhanced by meetings such as the Cast Record series, workshops on cave monitoring, and links to the wider Cast community. And of course, the S4 meetings are a new manifestation of that. And this sense of community was helped by the growing nature of the field and the very wide geographic possibilities for new speleothem research. So this business of team working is vital. In the team, well, the team that you can see there, for example, there are all-round cave scientists, laboratory specialists, talented equipment builders, petrographers, mathematical modelers. So you can see that the answer to this question about people, some people not wanting to be jacks of all trades, is cave science is multidisciplinary. Work with others as you need, and you can apply lessons you learned in your subdiscipline in a wider context. And the same thing applies to cave fieldwork. Now, the guy that's 4 people from the right in the photograph there is Chris Hawksworth, and he has always been a great promoter of teamwork, but he always made himself scarce when a cave visit was mooted. Now, I got stuck in, but I stopped short of vertical rope work. I didn't fancy that, while some groups, such as that at Innsbruck, is renowned for their speleological prowess. So in my first joint project with Christoph Spöttl, which resulted in our 2005 Geochemica paper, he was the overall leader. Anna Tooth brought her expertise in soil sampling and did the systematic sampling work in the cave, and I did the carbonate system modeling, although I did get through that squeeze too. Now, here's a whole bunch of problems: too many sources of uncertainty, spatial variation, unpalatable caves, complex caves, and here's a way forward. Let's eliminate the problems. Let's look at the factors systematically, evaluating them one by observation or experiment. Now, the role of such experiments goes back to Murray in 1954. And Murray grew crystals in the laboratory under controlled conditions and looked for controls of solution composition affecting the growth of aragonite versus calcite. And this was a direct response to the work that they were doing in cave science. Now, I expect you've heard of slow TV. So in Speleothem science, we have, let's turn this video on, here we are. In Speleothem science, we have a great candidate for slow TV in the form of slowly dripping water. Now, the context here are experiments conducted by Yiming Huang, who's here opening a constant temperature cabinet into which a precisely mixed fluid is fed by peristaltic pump. In this experiment, degassing is designed not to happen at the dripping point, which is a drawback, but the solution is supersaturated, and so after the drip falls onto a substrate below, calcite precipitates. The crystals were analysed by secondary ionisation mass spectrometry, otherwise known as the ion probe, at the University of Edinburgh, and the photo in upper the experimental setup and the methods of analysis were both innovative for the late 1990s, and the results on the controls of magnesium and strontium partitioning have proved helpful from the field. So an early example of experimental work, and there have been lots of great developments since, and one, for example, can mention the role of combining theory with innovative experiments in the work on isotope fractionation by Germany-based physicists, including Wolfgang Dreibrodt and Dennis Schultz's group. So here are, well, even more problems here. And we also can have a whole bunch of positive approaches to negate them. I mean, caves are natural laboratories, and we can take advantage of new analytical techniques. Cave conditions are constant or vary systematically with the seasons. Well, we don't know everything, but the things that we do know are positive and encouraging for us, and we can evaluate kinetics. We don't just have to throw up our hands and give up. So if we look, for example, at technique innovation, because of the broad context of Speleothem research, the role of technique innovation has been particularly spectacular. And here is a collection of some of the innovation. UV fluorescence, that was an early discovery by Andy Baker in his work. Multi-channel logging through the equipment building expertise of geochemist Dave Matty. Seasonal resolution using microanalysis, either ion microprobe on the lower right or synchrotron analysis on the lower on the lower left, but synchrotron analysis on the lower right, using micromills to seasonally resolve carbon isotope variation. This is by Ridley et al. 2015, and that's if you have a celluloid that grows sufficiently quickly. Soil gas and soil water monitoring. Of course, the multi-collector ICP-MS used for uranium series analysis and all kinds of trace element and other isotope analyses. Fluid inclusion analyses, lots of innovation there. So we have clumped isotopes, metal isotopes, sulfur isotopes, radiocarbon, nitrogen isotopes. The use of Climate Explorer to tease past climate scenarios. Climate system modeling, hydrological modeling, cave system modeling, sampling of aerosols, aquatic colloids, bacteria, organic biomarkers, DNA. All of these have been applied in Speleothem science. It's a very, very impressive list. But of course, a counter to this is sometimes the techniques don't work. The instruments break down. The results are puzzling or perhaps uninterpretable. I have vivid memories of, on 2 occasions, spending an entire week at the ion probe and generating results that have completely confounded what I expected and not at all helpful in completing the study. And in other cases where impressive time series had been produced by synchrotron radiation, and yet, despite weeks and possibly months of effort, I could find no correlations at all with climate variables. This is actually one reason why I say that I work on paleo environments, not just paleoclimates. Every worker will have tales of disappointment to set along the successes and partial successes that find their way to publication. But what about caves are too precious? Actually, and we've heard, of course, from George Venny just now about this issue, very, very important it is. It wasn't a major point of concern back in the mid-20th century, apart, of course, from preserving the appearance of show caves like this Grot Glamouz. Cavers and cave scientists could generally collect it well. Universities and museums built up collections of speleothems, but with variable quality of documentation attached to them. Here we've got examples from the University of Texas and the University of Auckland collections. So one response to caves are too precious is collect responsibly. Now, the meaning of collecting responsibly depends on the local context, but some workers have gone to the lengths of substituting sculpted replicas to replace removed stalagmites, and it is common practice to derive a preliminary age model from a drilled cord sample rather than sampling a stalagmite of unknown age range on spec. And another response is that you should be archiving your data. Data archives are really important for subsequent workers to understand what has been achieved and to build on it. And you know, there are these wonderful data archives. This one is based at the National Oceanic and Atmospheric Administration in the United States. This is their website. And they've also, in this one, gathering in data from the Pangaea site. Another response, again, is that of conserving remaining samples for reuse. Researchers are often very protective about material that has been collected and often often neglect to adequately archive the material for future reuse. There's always a need to go back and build on what has been achieved before. Concern about this led to writing this appendix in the Speleothem science book published in 2012. So although I have not collected a large amount of material in my research, material remaining from research projects at the University of Birmingham has been catalogued and deposited with the Lapworth Museum, to which the department's affiliated. There is a catalogue, and the materials are available for loan and additional subsampling to bona fide researchers. But the power of a research community to drive forward and celebrate innovation is so important. Here we see a group parading beneath sculptures of some great thinkers of the past. So, support your community, be positive, sign your reviews, embrace change, and remember too that in your careers you will belong to many different communities. So you need to be able to transfer your skills and approaches from one to another. And thankfully, the Speleothem world is rich in material to do this.